super excited to be here. Hello to everyone from all around the world. Thank you for coming. I am very, very excited today to present the topic of scaling out Airflow. Can you see the slides all right? Full screen, good to go. So today we're going to talk about scaling out Airflow. It's a topic that people have a lot of questions about. It is one of the most powerful features of Airflow to run on a distributed architecture, and we're just going to talk about overview and best practices for doing such. So we'll continue on. So my name is Alex, of course, and I am an Airflow engineer at Astronomer on our customer reliability engineering team. We do break fix support, all sorts of support tickets, advice, best practices, anything you need support on, that comes to our team. My background is as a data engineer. I've been doing that since I graduated from CU Boulder. I've done some data ops pipelines, infrastructure management, and my fun fact is that my whole career has been built on Airflow. So I started right out of college working with Airflow, and I've been working with it ever since. And I am an Airflow evangelist, you could say, where I am always excited to tell people all about it and try to convert them to the best data tool that I've ever seen. So let's just get started. Here's some key points of scaling Airflow, just some topics that we'll be discussing in this webinar. Airflow is virtually unlimited in the amount that it can scale. We use the Celery executor and the Kubernetes executor, for those familiar, to do that scaling. And once we scale, we need to tune parameters to fit the needs of our deployment. It's very easy to scale and add more capacity. We'll talk about that. And also, once we get to a point of scaling where we have maybe multiple schedulers, multiple web servers, this will be a topic later on, we need to make sure that all of our logging is in one place so we can do debugging and other troubleshooting things. So having all of that aggregated logging in one place is very, very helpful. I would consider it to be a necessity once we scale Airflow. So we'll continue on. Some high-level steps to scale Airflow. This diagram kind of just shows the main process of how we run Airflow at Astronomer. We start with building our deployments, we scale those deployments, and then we observe and make fine-tuning adjustments once we need to. And so the main topic we'll be talking about today is the middle step, the orange step, which is scaling. And we will also touch a little bit on the observe step at the very end when on the topic of that aggregated logging that I was talking about. Of course, there's more steps in between. We have a lot of, writing DAGs, debugging the scheduler. There's a lot of different things that go into running and scaling Airflow, but these are kind of the three main portions. So the first big question is, why do we even want to scale Airflow? It might seem obvious to a lot of data engineers, but maybe to people that are less familiar with the platform, why do we need to do this at all? The main reasons that we want to scale Airflow or any tool is because our workload outgrows our initial infrastructure. We plan and provision some infrastructure based on our expected workload, right? And as our team grows and as our business requirements grow, we need to scale the infrastructure and increase the capacity of our deployment. So we get more DAGs, we get more tasks, and also we do more intensive processing as our data sets grow. Another main piece why we scale Airflow is because the Airflow components need more durability and availability. And so what I mean by that is as we start to develop and run more critical workloads to our business, to our projects, we need to make sure that those are always online and ready to go. If your customers are expecting reports and those reports don't go out, then you're going to have problems. And so we need to make sure that all the individual pieces of Airflow are very durable and available at all times, as much as we can. Of course, the 100% availability will never be possible on any system, really, not guaranteed at least, but we get as many nines at the end of that 99.9 as we can. And there's kind of two methods behind the why, which is We can either scale in preparation for more DAG runs and compute load, or we can be elastic and save money and scale just as needed. So it's kind of about finding a balance between both of those pieces, because if we do too much preparation, it might be too expensive when we don't need the compute quite yet. And if we're too last minute and as needed, then we kind of miss opportunities to we add more fire drills, right? So if we get to a point where we need airflow scale and we need it now, there could have been some preparation that went into that first. So it's all about a balancing act between these two. So here's some symptoms to know that your Airflow deployment is ready to scale. There could be tasks that are stuck in a queued or scheduled state. You get unacceptable latency between tasks. So maybe you have a DAG with an SLA of 10 minutes and there's 2 minutes between each task before they actually run, right? In theory, if our tasks were instant, that leaves only space for 5 tasks, and maybe we have 20 tasks that need to run. So that latency can be a very big deal with DAGs that have short SLAs. And that kind of leads into the next point, when we're missing those SLAs because of the queued or scheduled tasks and the latency, that can be a problem. If you have high resource usage on your scheduler or web server, this is a problem because the scheduler will be kind of your bottleneck in the system and throttling the amount of things that can get scheduled. And once we get out of memory errors on tasks, we know that we need to increase some capacity in order to be able to process these bigger and bigger data sets. So if you've experienced any of these symptoms, it could be worth exploring the idea of scaling Airflow, and most likely that's what you'll have to do to be able to keep up with the workload increase. So if we're kind of just starting at the beginning, there's a couple of main principles that go into scaling systems, specifically distributed systems, which Airflow is a system that can be distributed across multiple VMs, multiple nodes. There's a lot of different methods for that. So if we're talking about the very basics of scaling systems, there's kind of 2 methods that we use in order to increase capacity. We have vertical scaling and horizontal scaling. Vertical scaling, like it says, is going to be increasing the size of the instance, adding more compute, more memory to a single instance. And then horizontal scaling is what we call scaling out versus vertical, which is scaling up. And the reason why we like to scale out is because you often get a better bang for your buck. It's going to be more affordable than just, an infinite increase of a single instance, because that's going to get really expensive really fast. And we'll talk about kind of when to apply each one of these techniques. This can be applied to Airflow and also applies to really any system that needs more processing power and more, horsepower, you could say. So with Airflow, if we're talking vertical scaling, this translates to adding more power to an existing worker. And what that means, when I say worker, it's going to be in Celery terms. If we're talking Celery Executor, that worker process, the worker node that actually runs the tasks. In Kubernetes land, that would be scaling up the pod that is running the task. And there's different ways to do that. We'll talk about that more later as well. But we would configure our executor basically with more power on an individual worker processor node. So like I said before, this gets really expensive really fast. And so it's worth vertical scaling to a certain point. But once you reach that point of diminishing returns where the price just gets way too much for the amount of power that you're increasing to, then it kind of makes sense to scale out. And so once we reach that threshold, which depends on your business, your budget, your use case, then we think about scaling out. And also we can think about delegating work to a dedicated processing engine. So that could be Spark or Dask or Ray, something that's meant for a single task to be spread out across a distributed system. Whereas Airflow is more meant for scaling out a bunch of tasks across the distributed system, but the tasks all run in one place. That's a whole different topic. And so the way that we run our tasks is not really what we're covering here. We're more so focusing on what it means to give Airflow more power for more tasks, more DAGs, and less so about the individual tasks themselves and how to be able to process more data. So just a summary here. It gets expensive fast. It's worth it to a certain point. And then we think about scaling out. So now we're talking scaling out. In Airflow, this means, and also really in any system, this means adding more nodes to your cluster. And so as we can see with this diagram here, comparing this to the last picture, I'm gonna go back real quick. This would be a transition of a single node scaling up on the right there. And then we can see down below, we have all these different nodes and the connections between them. So we're adding nodes to our cluster. This increases the maximum number of tasks and DAG runs that the system can handle. What I mean by that is as we move from 100 tasks to 10,000 tasks to 100,000 tasks a day, we need more space to be able to hold all those and run all those. And so when we talk horizontal scaling, this is a perfect fit for Airflow's orchestration model, because as an orchestrator, along with many other roles that Airflow plays, a lot of the time we're conducting the orchestra rather than playing the individual instrument. And so we're talking about delegating work to each individual piece, each task instance, and the work that gets done is most of the time done in Airflow. And like I said, Spark and Ray and those distributed tools can be used for the really heavy workloads. And so why we like horizontal scaling at Astronomer is because we get more power for less money than vertical scaling. And vertical scaling is going to reach a point where it's not possible. You're on the most powerful components, and there's no way to even go beyond that. Whereas horizontal scaling is basically infinite. You can always keep adding nodes, and as long as you have the networking set up between them. So at the bottom here, we see these black lines connecting all the instances. They have to be able to communicate with each other. It can basically be scaled as needed up to any point. There's going to be limits, of course, but in theory, I have yet to see a limit with myself and with our customers of how far we can really take this. And Celery and Kubernetes executors, as we've talked about, are really well designed for this horizontal scaling. So it's a great fit for Airflow. And I almost always prefer this over vertical scaling when possible. So now we can get
question there.
Yeah.
Sorry to interrupt
No,
you.
of course.
Can you talk a little bit about those symptoms that you mentioned earlier that indicate that you need to scale? Which of those sort of fit into horizontal versus vertical scaling? So for example, if I have a task that's running out of memory versus a bunch of tasks that are stuck in queued or something like that,
Yeah.
do you tend to point to one of these or the other, or are they sometimes both?
Absolutely. That's a great question. So if we're talking out of memory on a specific task, this is where vertical scaling comes in, because one task runs on one process, runs on one node. So scaling out isn't going to do anything for us in terms of giving that individual process more power. We'd have to scale up, right? And so when we're out of memory, that almost always leads to a vertical scaling problem or delegating work to a different engine. And so Airflow can be scaled definitely vertically very well. And for most data sets, we're not going to have to delegate work to Spark or something like Spark, right? Now, if we're talking about tasks being stuck in queued or scheduled, that could a lot of the time be due to this lack of scaling in a horizontal fashion, where we have more nodes delegated for more task instances, more DAG runs, right? And so, oftentimes too, our parameter tuning is going to play a big part in this as well, and we're going to touch on that in the Airflow specific section. And also our demo today is going to be about fine-tuning parameters and looking at a symptom of tasks being stuck and scheduled and queued. And so we'll get really in depth with that a little bit later on. But most of the time we're going to be scaling out. And then if we have specific tasks that need more power, then we're going to be scaling up. Hopefully that answers your question. Yeah. And now we get into the Airflow specific stuff. So this is what I get really excited about, because there are so many different pieces to this puzzle, and I've included some architecture diagrams to explain this a little bit better. What we'll mostly be covering today is the Celery executor, because we could do a whole lecture series on Kubernetes, right? Kubernetes is this beautiful, powerful tool, and when we're talking about scaling Airflow, a lot of times, and we're on the Kubernetes executor or running something with Kubernetes, then we're talking more in terms of scaling Kubernetes for Airflow rather than scaling Airflow itself. And it's a combination of the two. So we'll talk more about Kubernetes on the next slide. But for now, with the Celery executor, as we can see in this diagram on the right, we see an arrow that points from scheduler to workers, and we can see multiple workers in that stack. This is where the horizontal scaling comes into play. When we talk about scaling out with the Celery executor, we talk about adding more workers to our cluster. These worker processes run and process task instances. And so by adding those worker nodes, we're increasing the capacity of the tasks that Airflow can run. And so Airflow makes it really easy to add these as well. We just add a new process or a new node to our cluster. Like it says here, it can be a new node or an existing node, but we're basically adding some Airflow, not some, but the Airflow worker process to some VM, computer, bare metal, however you're running on-prem or in the cloud. We just add a worker, and as long as it can communicate with the broker, which is not on this diagram, and the metadata base, that's kind of those, when we talk about these black lines, that's the networking piece between and the kind of the connections between all the nodes, right? We could also do a whole talk about Celery executor. We have this, what I mentioned, the Celery broker, which can be Redis or another platform, and that is what actually queues the tasks. Just for a little more context there. And so we're not going to focus too much about the really deep underlying details. I think there's a lot of great information online about that, and from Astronomer and other sources as well. And mostly what we're going to be talking about is that, adding nodes and the basics of getting those connections between. So we need our Airflow home directory to look identical to other worker nodes. We have to have the identical configuration. We need all those connections to the broker and the database. Besides that, you're basically up and running. I mean, we just add worker nodes, and Airflow makes it very, very easy. It's a really graceful process, and the hard work comes in the parameter tuning more often. So opposite of Kubernetes, in the same line, but a very different tool, or sorry, opposite from Celery, I should say, we're going to talk about Kubernetes. And so, like I said, we could do a whole series about Kubernetes, and there's a really great document link that I left here when you get the slides at the end of the presentation of more details about the Kubernetes executor. A high-level overview is we have this cluster on the right that has the worker pods, and that connects to the database and the scheduler and the Airflow components, right? And so I would say the only thing that we really need to know for this talk is this cluster on the right, which actually runs the worker pods. Now, contrary to the Celery executor, the Kubernetes executor is running tasks as individual pods on a Kubernetes cluster. And so these task instance pods are ephemeral, just like Docker containers. In fact, oftentimes they are Docker containers that run on pods. Each task gets its own pod, like I said, and there are no dedicated worker processes. We have an individual pod for each individual task. And so when we're talking about scaling out Airflow with the Kubernetes executor, more specifically, we're saying, how do we scale Kubernetes itself? And which is why it kind of falls out of scope of the presentation we're doing now. I would really encourage people to take a look at this document and, contact your local DevOps expert if we're thinking about scaling Kubernetes, because there are a lot of important pieces that go into this that are out of scope of Airflow specifically. But it is similar to scaling with Celery. We're basically doing the same thing where we're just adding nodes to a cluster, and then Airflow with its connections to the metadata base and the executor and the queue that queues up tasks, we're basically just delegating tasks to more nodes. And so it really is, if we can call it simple. Of course, it's not a simple process, but it makes it as easy as it can be. Airflow is a very great tool for scaling on Celery or Kubernetes. Now we get into the juicy stuff, which is the parameter tuning. This is really the bread and butter of scaling out Airflow. There's a lot of really important parameters. There's going to be limiting factors, bottlenecks, and a lot of opportunities to really fine tune your deployments. And this will actually be what our demo is about. So we'll do a demo where we see some symptoms, we correct it with parameter tuning. So when scaling Airflow, these parameters, these 5 parameters, and of course, there's going to be more. So I included another link here for the reference of the configurations of Airflow. These are kind of the main ideas that I chose as the most important pieces. And these parameters control basically the number of tasks that can be run at a time. We can dig more into that sentence and say, we can tune the number of queued tasks versus scheduled, and we'll talk about that more with these individual parameters. But adjusting these in our Airflow configuration is going to be really what gets us to a great, smooth, stable point with our Airflow once we've scaled and added nodes. So first off, parallelism, the big overarching configuration that controls the number of tasks that can run at a time. It is exactly what it sounds like. It's the amount of task instances that can run in parallel across the whole deployment. And so when it says at the second sentence here, and I took this straight from the Airflow documentation, and there's more details on there about these different parameters. So definitely check it out if you have more questions. This value is the number of task instances in the running state in the metadatabase. Simple as that. So if we have tasks that are not running and they're stuck in queued, this would be my first place to check when I'm debugging. We're going to just go check parallelism and see, oh, we have 10 tasks running and our parallelism is set at 10. That is probably the bottleneck that is preventing more tasks from running. Next up, another important one is the max active runs per DAG. Also, exactly what it sounds like. How many active DAG runs can we have per DAG? If we notice that our DAG is not queuing and running more DAG runs at a time, this would be a place to look as well. And it can also, based on the number of tasks in each DAG run, can limit that the number of tasks that can run as well as the DAG runs, excuse me. A lot of times people set this to 1 because they have tasks that depend on the previous run. There are other ways to do that. But if we really design our Airflow system in an idempotent way, where each DAG run represents a specific instance in time, each DAG run is repeatable and gives the same output every time. I did not include anything about idempotency in this presentation, but it is a core principle of tools like Airflow, and I would encourage people to look into that as well. I'll post that, or I'll have probably Kenton post that in the chat. It's kind of a weird one to spell. And there's great resources online for that as well. And so, yeah, this one's also pretty straightforward. Max active runs per DAG. I would say whoever named these parameters did a great job because they're all straightforward based on the name. It's great. And so I don't even really have to explain this one that much either. It is the max active tasks per DAG. And this is the max tasks in the active state, which can be queued or running. That's a very important distinction because if we have tasks that are not going into queued, but they're scheduled, that is controlled by this parameter also. It's not just running tasks. So just to repeat that, very important note, active means a task instance is either in the state of running or queued. If we dig a little bit deeper, once a task is considered active, it is no longer really the job of the scheduler. The scheduler has passed over, delegated the work to the executor at that point, and the executor is going to pull off of the queue and get through tasks as it can. Now, I had one more piece about this, which is the last sentence there, where we're talking about stopping a DAG with an early start date from stealing executor slots in the cluster. This is what we mean when we say this is that the tasks get ahead in the priority queue if they have an earlier start date, because we want to make sure that we're running stuff in the past. And so if we have an early start date, maybe some backfill things that are happening, it can hog executor slots. And so we can limit a DAG and let other things run as well. And it's all a balancing act of what tasks you want to be able to run and have priority. And there's more parameters, again, that are surround priority and the queue itself, but this is really the big piece. We also have worker concurrency. If we see tasks that are stuck and scheduled and are not moving to queued, this is another piece to look at, because this is the number of tasks that can run on an individual worker at a time, and it limits your tasks so your worker doesn't get overwhelmed. So we size up our workers based on resources on the worker box and the nature of tasks, as it says. And it really is just the number of tasks that a worker can take at a time. Queued or running, which remember we define as active. So the max active tasks per worker. Pools. This is another way we can control more fine-grained control of how groups of tasks are running and the concurrency of groups of tasks. So a pool is basically, it also considers the active tasks, and it's a limit on the number of slots that a pool has is the limit of the number of running and queued tasks that pool will allow to run at the same time. This is another tool to circumvent the executor slots being hogged by heavy DAGs with a lot of tasks. Like I talked about with the early start date, we have tasks that can really clog up and bottleneck our system, and we can put those into its own pool and limit with the pool the amount of active tasks that is at the same time. But we can also do it across DAGs, right? Worker concurrency is individual for a worker. Max active tasks is individual for a DAG, and pools allow us to kind of combine those things together and group multiple DAGs or multiple groups of tasks into their own concurrency pool where we can control that. To size pools, you can do it through the Airflow user interface. There's in the pools, you go to admin and pools. I'll show that in the demo. You just click an edit or an add action, and it lets you add a new pool. You can configure tasks to go into that pool and things like that. Taking a step back from workers and tasks, we can also talk about the high availability of Airflow components, which is something that was introduced in Airflow 2. Really great feature. Other Airflow components besides the worker pool can also scale. Scheduler, so Airflow allows for multiple schedulers, increases the capacity that the scheduler can handle when it's scheduling and delegating tasks. And it adds more stability. If one of your schedulers goes down and you have your other scheduler in a different availability zone, that gives you more stability in your platform, which we talked about in the key takeaways earlier in the presentation. And it's something that's very important, because if you have one scheduler, that is one point at which your Airflow deployment can break and everything stops moving. So by adding more schedulers there, we can increase that durability of our system. We can also
get a relevant question on this from the audience, but somebody asked about, sometimes their scheduler becomes idle, or they notice like a heartbeat isn't running or something like that. Yeah. Is that something where either, insufficient memory or resources might be at play there? And also, is that something that, running multiple schedulers with Airflow 2 would help with?
Yeah, I would say that's a complicated one. It really depends. A lot of times, if your scheduler is idle, that leads me to believe that there's some sort of parameter configuration that's not tuned right. It can be a resource contention problem. So if you're running the scheduler on a node that's throttling on CPU, right? Your scheduler can kind of grind to a halt if you don't have enough CPU cycles to allocate to the scheduler process itself. I would look at parameter tuning first, definitely. And the scheduler logs are going to tell you a lot of clues. We're going to talk about that in just a second, but 90% of the time when we have problems with our scheduler, with our tasks, the parameters, the clues will be found in the scheduler logs. So that's why the logging and the debugging steps are really important here too. So it is a complicated question, and the answer that no one wants to hear, it depends. I say parameter tuning, look there first. Think about scaling your scheduler up first. And if you're having problems with the durability, then scale your scheduler out. There's kind of a balance again between scaling scheduler up versus out. And it does take a lot of experimentation. That's kind of one of my other key takeaways I didn't note is don't be afraid to experiment on your dev cluster and dev deployment, and really tune this before you get to prod. I always will advocate for having multiple levels, multiple priorities of deployments, dev, test, prod, dev, stage, prod, whatever that looks like. Having places to test things first in a production-like environment is really important for debugging issues like an idle scheduler or something like that. And then where we left off here is you can also scale the web server up. So up or out, you can have multiple web servers. You can scale your web server with more resources, and that can kind of speed up the rate at which your web server loads pages. Maybe you have a big tree view that's hogging a lot of resources, trying to render all these tasks in a graph, or and graph view can also do that as well. So something we'll touch on real quick is the logging piece. And so when we're talking about logging, there's a few traits in my experience that make a really great logging system. And so the logs are aggregated, meaning if you have multiple schedulers, you can look at the logs for those schedulers all in the same place. We have historical logs, meaning we can look back in time and get events that have happened, whatever your retention is, whether it's 2 weeks or a month, kind of tuning that as needed, but being able to look back when we have problems and take a week or two if we need to debug that, and saving those logs is really important. And then indexed and searchable, as you can see in this picture on the right, I have this system where I can search for the scheduler component. I can search for individual messages in there, patterns and messages, and we can see that all the logs for all the schedulers kind of get lumped into one place. And when you have, like it says here, 2.7 million log messages, and this is just in the past 15 minutes, it's really important to be able to search through that. There's a very high volume of logs, and this is multiple deployments aggregated together. You're not going to have realistically as many logs as we're seeing here in 15 minutes, but it's still more than a human can reasonably read through. And so being able to search those logs is really important. Like I said, 85% of problems, and I have a little bit of a mismatch here. I changed it to 90 because I got more confident that the scheduler logs are a really great place to look. And so I would change this 85 to a 90%, if that makes any difference. And it's important to have, if we have multiple schedulers, to collect all those logs in the same place, like I said, and those components are all working together to get to the same solution. So we keep a history of the logs in a way that we can search it. And then when I'm debugging customer deployments at Astronomer, my first steps is always to correlate task logs, scheduler logs with the same timestamp and see if there's messages or clues happening between those two pieces. And so having this really great logging system when we start to distribute, getting all of our task logs in one place, getting all of our scheduler logs in one place, and being able to search through and correlate these, there's a ton of information in there that's really great for debugging. And like I said, the 90% of problems have clues in the scheduler log. I put 8% of problems. So a much smaller piece, but still important, is resource consumption issues. So if you're out of memory, if your tasks kind of grind to a halt and move really slow, you might want to think about scaling up, right? The other 2% is the challenging part, where there's not always a lot of logs, and it requires more digging. And so this 2% is the type of work that we do on the CRE team. And so we're taking on the really hard problems and bringing in experts, right? And to be able to solve these really challenging airflow problems. And oftentimes there's workarounds, but as we get more and more into the debugging process, we learn to discover patterns and kind of we get good instincts about these first problems. About these hard problems, I should say. Yeah. So now we get to the demo piece. Ken, should I just get right into this, or should we do some quick questions about any slides?
Yeah, I think dive into it and we'll leave maybe 10 minutes,
Okay,
10 or 15 minutes at the end for questions.
perfect. So I'm gonna stop my share real quick and get my Airflow deployment all ready to go. Log in real quick. Okay, I think we're good. So I'm gonna share my Chrome page and let me know if you can see my Airflow deployment. Good, great. So if anyone has seen the tree view before, this brown color can be a problem because it means that the tasks are scheduled but not running. Now, of course, my DAG is paused right now, so this makes sense. The scheduler is not going to actually queue these tasks until the DAG is unpaused. So let's unpause this real quick, and let's kind of watch our DAG execute. These are just a bunch of tasks that sleep for different amounts of time. We have a quarter of a second, 1 second, a minute. And we can see all these tasks, they just sleep and they don't, it's basically a no op, but it is a bash operator that sleeps. And so, well, actually it's a Python operator. Doesn't really matter for this context. And so we can see we have all of these tasks scheduled, right? And only a few of them are in running and then a couple of them are in queued as well. And so what we see here is, what I'm wondering when I first look at this is why are there so many tasks that aren't running or queued? Because all of this is doing is sleeping. It's basically a no op. We should be able to run like 1,000 of these at a time, right? And so there's something that's bottlenecking this system, right? And so kind of my steps for debugging these symptoms are going to be to start with the configurations, and we'll take a look at pools too first. So it can be helpful here. So we see there's 15 running slots, right? And if we refresh this a couple of times, 15 plus 1, so our new max is 16, right? And we kind of want to know what the number on that bottleneck is. So we've seen 16, we've seen 15, 13, and we'll just take the max of that. So we'll just kind of right now, there it is, operate under the assumption that 16 tasks is the max that can be running. We see there's 128 slots in the pool, so that's not a problem. And we see in our configuration, so I guess pausing for a second here, we can see pool is not limiting us because we have 128 slots. There's a lot more space for this to run. So something else is happening here. I'm going to go into my configurations now. And I'm going to do a quick search for one of those parameters that we talked about in this presentation, which was parallelism. Parallelism is 10,000. So that's not the problem. We should be able to run 10,000 things at a time. And so the next thing I would search for, if we go back to our DAG here, and I'm just going basically down that list of parameters that I talked about and just checking, is this the bottleneck? No, move on to the next one. Max active DAG runs doesn't look to be a problem because there's like 100 of these and they're all unscheduled. So if we go back to our configuration, if we look at max active runs per DAG, it's at 150, right? And now we also see max active tasks per DAG is 16. So we talked about that 16 before, and now we're seeing 16 right here. And so this looks to be a fix to our problem. If we just change the max active tasks per DAG, we should, in theory, get more tasks running in that DAG. And so we're going to hypothesize that this is the configuration we need to change. So I'm going to go back to my, this is our Astronomer software. So for our, one of our products at Astronomer here. And so if I go into my, my playground deployment, which we're on right now, I have this set, and of course I planned this to happen, so I set this to 16. So if we're gonna go in here and edit this, I'm gonna change this to 100, and it'll change to 128. So we're gonna be maxed out now. Remember, our pool was also 128, and our max active tasks per DAG is now 128. So what we're expecting to see is 128 tasks in the active state at a time if our hypothesis was correct. So I'm gonna deploy these changes. And I'm also going to come back here and talk about something else. Another symptom that we are going to see, and we don't have a ton of time, and this deployment takes a couple minutes. So what I'd like to do is kind of give a little precursor, a little foreshadowing of what we're going to see next. You might notice there's one parameter I didn't check on that list, which is worker concurrency. And I'm on the Celery executor, as we can see here in our platform, with one worker. And so if we think about, if our worker concurrency, let's check it, is Also 16. Uh-oh, we have another problem here. So it's kind of worth checking all these parameters at the same time and making those deployments as needed with the change. So what we expect to see here is now more tasks will be transitioned into queued, but they won't actually run because the worker concurrency is limiting it. We have one worker times 16 tasks per worker. We're going to be stuck at 16 still, but it's going to look a little bit different. And so I'll show you how that looks different. If we noticed the symptom originally, when we ran into the bottleneck with max active tasks per DAG, the symptom was that a bunch of tasks were stuck in scheduled, but there weren't a lot of things in queued. Once things got to queued, they started running. And so we'll kind of wait for this to come back online, and we'll go back to our DAG here, and we can see, if we go back, whoa, there's a bunch of stuff in queued. So now we've reduced the number of scheduled tasks. That was our first symptom, but now we're limited by the worker concurrency again. So we have another problem with our configuration, right? But we've made progress, and we've moved tasks further down the line. And so we've gone from scheduled to queued, but we can see about 16 tasks here, which we've talked about as the worker concurrency. Those are the only ones that are running. And so if we wanted to get more tasks from queued into running, we'd have to actually adjust that worker concurrency as well. Or we could add more workers, and that would also increase capacity. We're going to do both. And so what we're going to do is now change worker concurrency to 32. So looking at these numbers, this is still the lowest. So it still is the bottleneck. But also what we're going to do, go into, oh, sorry, I have to deploy here. And we'll just stick with this for now. So what we're expecting to see now is there's still going to be some stuff stuck in queued, right? Because we have 128 max active tasks and 128 slots in our pool. But this worker concurrency is limiting us. But so we can confirm that this is the bottleneck. By now we should see things that are still stuck in queued, but there will be more tasks in the running state. While this is deploying, I'm going to give a quick disclaimer. This is a ton of information. If you don't understand the specifics, that is totally okay, completely fine. The really important piece here is to think about the process that I'm using to debug, right? I'm using the scientific method of making a hypothesis, changing something slightly and keeping control variables, and then testing that hypothesis and coming up with new plans after, right? That's the really important piece with debugging and tuning parameters, is we want to basically just change one piece at a time and check the symptoms again and see what happens, right? And so if I refresh this, we'll see if this is going to be deployed yet. So let me go back to my configurations. Worker concurrency is still 16, so we haven't quite deployed. And we'll wait for this just for a second. Airflow, celery, worker concurrency. Yep. So this will take just a minute to come online. So the really important thing is the process of debugging rather than the specifics. People talk about not enough people to manage resources on our team, difficulty managing supporting infrastructure when they're talking about scaling Airflow. And if we can tune these parameters just right and use this process of debugging, it gives your people on your team more resources because we have a really good process of debugging. And then we don't have to worry about infrastructure as much because we can get every last drop of performance out of our single worker. And that's enough. We don't even need more infrastructure, right? And so by following these debugging steps, that's why I think this demo is so important for this topic, is because it gives you a really good process of what we learned in grade school, or what I learned in grade school, right? Which is that scientific method. We're just applying that to Airflow as well. And we'll see if we can we're still stuck at 16 here, so I'm not sure why we're not deploying. What I have a feeling is, here we go, 32. First, this is our Airflow CFG, that's right. And our environment variable is actually controlling this, so don't worry about that. We have the correct configuration now. And if we go back to lots of queued, we can go into our running again, and we should see a lot of stuff in queued still, but look, we have way more stuff running at the same time. That's amazing. And if we go to our pools again to kind of check this active task thing, we can see our running slots is 45, which is like even more than we expected. So the worker concurrency is no longer our bottleneck, right? But we've increased in 2 steps, in 2 parameters. We increased the number of scheduled tasks that can move to queued, and then we increased the number of queued tasks that can move into running. And we did all of that without scaling any infrastructure. So that's the important bit of parameter tuning. I think that's probably where I'll end this demo. I know it was like lightning fast, tons of information. This will be recorded. I suggest if you have more questions about these, like if you're like, I've experienced this symptom, I need to know how to fix it, rewatch the webinar, rewatch the demo, and pause when you can and test things. Hopefully this gives a little bit more insight into how I do my job of debugging and how, as we scale Airflow, we can follow that process through.
Awesome. Thanks, Alex. That was so much really good information. Obviously, this is a huge topic and it's not possible to cover every possible scenario within 1 hour. We would keep everybody here all day, but we do have some good questions in the chat, so we'll dive into those during our remaining 10 minutes. The first one I think is a really great question. Michelle asked, can Airflow scale to a large number of DAGs? And by large, I mean like hundreds of thousands.
Ooh, great question.
This is a really good question. We see this come up at Astronomer a lot. Yeah. Hear your take.
That's a great question. And I have to be totally honest. I wouldn't really know off the top of my head without testing. I talk about virtually unlimited. In theory, my answer is yes. However, there are a lot of limiting factors in terms of networking and the computing itself, right? Like the underlying details of how computers work themselves, right? That could be a limiting factor here. I would say if you're interested, just try it and see what happens. I mean, that's the type of thing that interests me, right? Is just to experiment with that. And I would say, yes, in theory, we could scale as much as we want. However, I have seen instances where there are way too many DAGs to run in a reasonable fashion if you don't have like unlimited budget and capacity, right? And so oftentimes we can think about situations where, obviously this is probably a theoretical question, but are there situations where we really need 100,000 DAGs, or could we squeeze that into less DAGs and more tasks? That makes a difference as well. I mean, overall it's the same number of tasks, but it can kind of be consolidated into more manageable bite-sized pieces for DAGs. So overall, I would say that's a great question, and I'm curious to know the real answer to that, right? Because that's the type of thing that I also do at Astronomer, is when customers come to us with questions like this, we do the testing for them and find the answers to these really broad edge case scenarios. So hopefully that answers your question. I know, again, it's not the best answer of like maybe, but in my experience, in theory, it should be possible. So it's pretty exciting.
I think that's a great example, and what applies to sort of all of this is that this is often more of an art than a science. Mm-hmm. And unfortunately, there aren't specific answers of this always works. Just from my perspective in the field, we have certainly seen Airflow deployments that had thousands or even 10,000 DAGs. I don't know that I've seen 100,000 in a single Airflow instance. That may be a reason to break it up. Somebody asked if you switch that over to more tasks and fewer DAGs, do the tasks just bottleneck? Not necessarily, because there are other processes in place going on behind the scenes within Airflow of those DAGs being processed, and they have to be rendered in the UI and all of those things that come into play there as well. So there's a lot of balancing that goes on with that. Absolutely.
And it really is this beautiful, I love the art more than a science. It's such a beautiful combination of those two things where you get this instinct, and by experimenting, we start to get this instinct of like where to look first, and we come up with better solutions faster the more we play with it. And so I really encourage people, if you have the spare time and the chance, to test these really hard-hitting questions you have and discover more about Airflow and really explore. There's so many facets to this product, right? And there's so many ways. Like I've been working for 3 years straight just on Airflow. I learned something new pretty much every day about Airflow. So
another question in that vein, we asked, are there sets of config parameters that are known to work for a given scenario? This is one where I'll let Alex answer in a second, but from my perspective, it's definitely more of an art. I feel like the unfortunate answer is usually not. It depends so heavily on what your DAGs are doing that if we could give you these are what you should set all of your Airflow config parameters too. I would love it if we could do that, but I certainly don't have one.
And I would even go so far to say absolutely not. The reason why I would be so confident with that answer is there's so many factors that it depends on. I would say, like you said, Kenton, if there was a way to do this, I mean, we could say you have 5 workers, 100 DAGs, 1,000 tasks. These are your numbers. But then if we think about it, it depends on how heavy these tasks are. How much data are you processing? How many tasks per DAG? How many DAGs total? Excuse me. How many, um, what's the instance size of your AWS nodes for your Celery worker? Are you on GCP? Maybe the instances are slightly different and the CPUs are different and they have different clock speed. I mean, there's like so many, it's such a, so many esoteric examples of how these can differ that I would say, rather than looking for specific numbers, do that experimentation and really find what works for you, because every deployment is going to be a little bit different. And so there can be good standards, and also you're never going to find the perfect numbers without actually doing some testing and experimentation.
Yeah, definitely. A great question. Someone was, do you have any books or other resources that you recommend on Airflow scaling specifically?
That is a great question. I actually do. So I don't have any books about Airflow specifically. I do have books about distributed data systems though. And so I might have it right here. I love talking about this textbook. I think it's like data intensive applications, and I can link that, but it's a great textbook about really fine details of databases, write ahead logging, concurrency, eventual consistency. I mean, there's so many different topics about data, and a lot of that can be applied to Airflow as well if we're talking about these big distributed systems. And I'll try to find a link for that and throw it in the slides as well, like in an extra resources page, because it's been one of the best textbooks I've ever read in or out of school. I mean, it's been a great find. Mark Lamberti, all of his stuff is fantastic. Before he worked at Astronomer, he's the one that taught me Airflow, and he's, a big data engineer, in his past, and now he just teaches Airflow because he knows so much about it. And I would say just, Google Stack Overflow if you can find the right people. Medium is a really good source as well if you have a Medium subscription. It's hard for me to really recommend these third-party things because I can't really fact check everything. But just doing independent research about your individual questions, people oftentimes have really good answers just on the internet, and it can be hard to differentiate the experts from the not so experts. But there's a lot of good resources online as well. So I would say the data intensive applications textbook as a base, as a data professional, is a really good place to start. And it's dense. I mean, it's like 600 pages of pure theory. It's awesome.
That's awesome. Well, I know there are more questions that we didn't get to, but we just have 1 minute left. Again, I said this is a huge topic, so we could keep going all day. But definitely want to thank everybody for joining. I will also throw out there, I know there was a lot of conversation in the chat about scaling your Airflow database and the connections there. That's another huge topic that could certainly be its own webinar. If you want to talk more about things like that, especially as it relates to the Airflow open source project or any other questions that we didn't get to, please feel free to reach out to us. We'd love to talk to you here at Astronomer about all of these Airflow things. And we will definitely think about those, other conversation topics for future webinar topics sort of within this same vein. So
that is a really, really great point. Just real quick, since we have about 30 seconds, I just want to say all of the stuff that I talked about today is making the assumption that your database is in good shape for an unlimited amount of scale. And that's obviously not realistic for you're not going to have an unlimited size of database, but I would say that definitely two very different topics, and it could be a good supplemental webinar, something to think about for the Astronomer team as well.
Yeah, for sure. Well, thanks, Alex, so much for sharing all of your great knowledge from your experience with this. This was super helpful for me, and I'm sure for everybody else. And Yeah, look forward to webinar recording should be in your inboxes coming up, and we'll look forward to seeing you at the next one. Thanks for joining, everybody.